We are discussing periodic classification, and we are actually linking all the applications, and we are banking on some of the applications because these will be questions in the exam. Right, today we will like to deal with, a direct consequence of shielding effect. Right, direct consequence of shielding effect, that's nothing but Lanthanide contraction. Let me tell you that you will be getting a question in this. You will be getting a question in this. Please bank on it. The direct consequence of a shielding effect is, of course, what? The Lanthanide contraction. And let us discuss in detail and what are the questions that we expect from what? Lanthanide contraction. You must understand. As we deal with periodic classification, I would like to remind you always, I would love to remind you rather, right? It's a serious thing. And people who are good at periodic classification, the entire chemistry revolves around it. So people who are good at periodic classification are normally good at what? Chemistry. You must understand this. So it's not trivial. It's not silly. No one has asked you to place this 120 elements in the periodic table as you like randomly or something like that. Absolutely not. This is done with schemes, rules, principles, right? There is a way out there. It's not randomness. And there are some properties which repeat themselves at regular intervals. That is done only when you do it with some rules and principles and schemes. Otherwise, they don't repeat at regular intervals. And the most striking feature is, the seventh period is incomplete. Well, you have infinite number of shells in an atom, and each shell is a period in the periodic table designated by the principal quantum number. So when you have the principal quantum number valuing from n is equal to 1 to n is equal to infinity, then I think you can expect an infinite number of what? Shells even in atom. Right? You have infinite number of shells even in a period also. And I think it leaves a scope for you to go out, check out, discover an element, and I have a place for you in the periodic table. I have a place for you in the periodic table there. So it stimulates research. It's not simple. And one more striking feature when we are dealing with what? The modern periodic table is it has 18 groups and 7 periods, and the 7th period itself is incomplete, and you have infinite number of what? Periods waiting for you. Go out, discover an element, put the element, and I can judge the physical and chemical properties of that. And the modern periodic table is also telling us is, the physical and chemical properties, which I define it as a mode of activity, which I call that to be a mode of activity of a particular element, right, is all dependent on the atomic size. As I said, I always say in the first place that, what is the difference between all the elements that are placed in the periodic table? Then don't look here and there. You don't need to think. You don't need to think something else except for the atomic radii. You must understand the atomic size. It is atomic size which will basically determine all the mode of activities of all the compounds. And if you see from the beginning, if you look into the periodic properties, what we are dealing with, say it's electropositivity, electronegativity, electron affinity, or even ionization potential, or whatever, these are all functions of what? Sizes, right? The size variance in the period and group will determine the mode of activities of these elements. And today, I was telling you, there are several questions which you need to bank on, and those questions will come in exam. Well, I would like to put that all at one place, but today's discussion is basically Lanthanide contraction, which is it's a direct consequence of what? The direct consequence of shielding effect. Now just recollect what is basically shielding effect. Shielding effect is if in between a nucleus and the outermost shell, if in between a nucleus and the outermost shell, if the number of shells increase, if the number of shells go on increasing, then the nuclear force of attraction, right, that is falling on the outermost shell will decrease, because we understand that the electrons which are there in between the nucleus and the outermost shell are basically shielding them. Shielding what? The nuclear force of attraction. Thereby, the outermost shell starts relaxing if you have more shielding effect. When you're relaxing, the atomic size is increasing rather. If you're actually pulled down due to a bad shielding effect, then I think you are pulled towards the nucleus, thereby the size decreases. So what is basically shielding effect is, look here, this is the nucleus, if in between the nucleus, and this is the outer shell. This is the outer shell, right? Between the nucleus and the outer shell, if the number of shells increase, If the number of shells increase, when I say number of shells, I also refer to what? Number of subshells. You must understand. If the number of shells are increasing, even the number of what? Subshells are increasing. You must understand that. Right? So between the nucleus and the outermost shell, if the number of shells are basically what? Increasing, then the nuclear force of attraction, which is supposed to fall, the nuclear force of attraction, NFA, it's not nuclear force. Don't substitute nuclear force for nuclear force of attraction. I was telling you always, nuclear force is that which is present inside the nucleus as a short range force. Nuclear force of attraction is that it's there between a nucleus and the outermost shell. You must understand that. Don't substitute one for the other. So, in between the nucleus and the outermost shell, if the number of shells increase, then the nuclear force of attraction, or I can say the effective, or I call this to be resultant. The resultant nuclear force of attraction that falls on the outermost shell basically decreases. When you decrease, this tries to relax. That tries to relax. When it tries to relax, I think the size will be what? The size increasing. So I understand that when the shielding is more, the size is more. You must understand. So I can actually say shielding effect is directly proportional to what? Size. You must understand. Greater the shielding, more will be the size. You must understand. And lesser the shielding, lesser will be the size. You have a direct relation between them. And also recollect, it also has ionization potential getting affected, and it is directly proportional to the shielding effect. And also remember that ionization potential, in fact, I also say that shielding effect is directly proportional to what? Size. Remember these two. So they have a relation, exact relation between these two. IP inversely related towards shielding effect. So greater the shielding, the ionization potential will be less because the size will be more. That's what is shielding effect. Just recollect what we are telling. So before I go to the Lanthanide contraction, where you can bank the concept of what? Lanthanide contraction, where you can bank on the concept of Lanthanide contraction, you can expect at least 2 questions in all the pre-engineering tests or pre-medical tests which you will be writing. Right? So let us conclude what is shielding effect. Then between the nucleus and the outermost shell. Look here. Between the nucleus and the outermost shell, if the number of shells increase, then the effective or the resultant nuclear force of attraction on the outermost shell basically decreases. When it decreases, then the outermost shell tends to relax. When it relaxes, the size is basically increasing. So greater the shielding effect, more is the size. More is the size, ionization potential decreases. You must understand that is about shielding effect. And also, I would like to add to this. In fact, electrons present in S are better shielders compared to P, compared to D, compared to F. You should understand. So if the bulk of the electrons in between these shells, right, are present in S and P, they are better shielders. If they are present in D, the shielding effect decreases. And if you come to F, I was telling you to view F, it has a very peculiar diffused shapes. I call the F subshell to be having a peculiar diffused shapes. Peculiar diffuse shape. That means that the F orbital might be having some pores. So it's a very bad shielder is what? F. So it all depends on not only the number of shells that are present in the nucleus and the outermost shell. Understand clearly. If the number of shells between the nucleus and the outermost shells are more, the shielding effect will be more. But that's not all. That's not all. We need to tell the bulk of the electrons are there in S, P or D also affects what? The shielding, you must understand. If the bulk of electrons are present in S and P, I think the shielding effect is more. And if the bulk of electrons are present in D and F, I think the shielding effect decreases and the outermost shell relaxes. It relaxes. You must understand that. Right? So I gave you full information about what shielding effect. And finally, let me conclude. Between the nucleus and the outermost shell, if the number of shells increase, the bulk of the electrons are added to S and P, then the shielding effect is more, right? and if the bulk of the electrons are added to D and F, right, and then the shielding effect will be what? Lesser. In the first case, the size will increase. The second case, you don't find the size increase because the outermost shell, the relaxation has been capped. You must understand. That is the shielding effect, and this is the trend of how the shielding effect will be varying. Now coming to lanthanide contraction, watch carefully here. Now what I'm writing here today, I think this is 100% sure question in exam. This question, you will get it in exam. Whether it's an advanced level exam which you are writing as a JEE Advanced or any other pre-engineering test, the questions will be asked in lanthanide contraction. So please listen to me extremely carefully. Watch carefully here. Now remember, when we are actually framing the periodic table, right? When you are framing the periodic table, then it is somewhat like this. Watch. You have two groups to the extreme left, and that is 1A and 1B. And these are called S block. The S block, that is alkali and alkaline earth metals. Look at the geography such that you can understand lanthanide contraction better. What we are discussing, let me be clear first. What is our point of discussion is lanthanide contraction, and which is a direct consequence of a shielding effect. This is the discussion which I am making, and the applications of lanthanide contraction are 100% sure questions in exam. That is the discussion which I am making. And why I am drawing the geography of the periodic table is to locate the lanthanides first. Forget about lanthanide contraction. Where are the lanthanides? Let me check that first. Right? And remember, in between you have the D block. And then finally to the right, you have P block. You must understand. So these are two groups. These are 10 and these are 6. So D10. So 10 plus 6 is 16 plus 2, 18. So you have 18 groups. Mind you, you have 18 groups and 7 periods. That is the long form of the periodic table. Now observe carefully. When you have 7 periods, the first, second, third, fourth, fifth, I have no issues. I have no issues. Now coming to the 6th period, I draw the attention of everyone. Where are lanthanides? Look into this question, what I am writing first. Where are lanthanides? To which period they belong? To which period they belong? And from which atomic numbers to which atomic numbers? These are the basic information you must be having first. Where are lanthanides? Coming to the point. Now the lanthanides actually are starting in the 6th period. 6th period. You must understand. They start from what? 6th period. You must understand that. Right? And remember, in the 6th period, lanthanum, after lanthanum, which has an atomic number 57, lanthanum, which has the atomic number 57, this lanthanum belongs to D block with atomic number 57. Let me write it correctly. This is a 6th period which I am writing, and it is lanthanum. It's lanthanum with atomic number 57. And I want to warn you, and I want it to be very clear, lanthanum is a D block. Lanthanum is a D block element, this D block. Till now I am not telling about lanthanides. I have not discussed about lanthanides. What I am telling is, you have 2 groups to the left, 6 groups to the right, and in the D you have 10. Total are 18 groups. You have 7 periods. And I am taking the 6th period. I am taking the 6th period. Now it's like this. 1st period, 2nd period, 3rd period, 4th period, 5th period and 6th period. In the 6th period, I have lanthanum with an atomic number 57, and it belongs to D block, and it belongs to 6th period. I'm underlining. This is the 6th period and lanthanum with atomic number 57. And watch if it is D block, and if I can write it here for you, if this is lanthanum with atomic number 57 because it belongs to D block, right? And after lanthanum you're supposed to get 58, an element. But if you actually open the textbooks and see, 58 is missing. If you actually go and check a closer look of the periodic table, then after lanthanum, where you are supposed to get 58 as the atomic number, you will find 72. Observe carefully what I'm telling. I wanted to spend as much time as possible here, until you understand. Remember, this is the periodic table, this is the S block, this is the D block, this is the P block. This is the P block. P block has 6 groups, S block has 2 groups, D block has 10 groups. So the total account seems to be 10 plus 2, 12. 12 plus 16 is 18 groups. We have no dispute in it. That is how the long form of periodic table is. That is about groups. Now forget about groups. Coming into periods, the horizontal lines. When you go for periods, this is the 6th period element, that is lanthanum. What I'm trying to tell is lanthanum is D block. Lanthanum is D block with atomic number 57. This is the 6th period, 57. But if you open the periodic table and see, we expect after 57, 58. But for your information and for your surprise, after 57, immediately in the 6th period, you get 72. 72. So if I can subtract 72 minus 57, there are 14 elements that are missing. And remember, these 14 elements are following lanthanum. 14 elements that follow lanthanum. Lanthanum is D block. That 14 elements that miss the main frame of the periodic table are put at the bottom. And that is from 58 to 71. And the 58th element is cerium. And the 70th element is lutetium. These are pulled out from the main frame of the periodic table. And they belong to 6th period only. They belong to the 6th period, but kicked out from the main frame. And now, 2 things you must understand. Lanthanum is a D block. This is D block. Whereas these fellows, it is filling F block, 4F1 to 4F14. Because F can accommodate 14 electrons. And since after D, immediately the electron is entering F, between D and F, the decorum of the periodic table is lost. The harmony is lost. Because in lanthanum, the electrons enter D, D1. Then we expect 58th element to be D2. Then we expect this element, cerium, to be D2. But the electron won't enter D, it enters F. So if it is D1 and if it is F, the entire decorum of the periodic table is lost. And I spend as much as time as possible for you. Go home, open the periodic table. What you will find is lanthanum is a D block element belonging to the 6th period. And the electron will enter D1 there, D1, 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 D1. If you write the electronic configurations for 57, electronic configuration for 57, it will enter D1. Then we expect the element that follows lanthanum should be D2. That is this element, because this is 58. Instead of entering D, it enters F. Then it's a mix-up. It's a mix-up and the decorum of the periodic table is lost. The harmony is lost. So what people have done, since immediately after entering D, it is entering F, it is kicked out from the mainframe of the periodic table. It's kicked out. It's kicked out from the mainframe of the periodic table and put it down. And now the electrons will enter 4F, fill all the 14 from cerium to lutetium, and these are called F block. And these are called lanthanides. So lanthanum is a D block. Lanthanides are what? F block. I repeat this statement. Should not be any confusion. Lanthanum is a D block. The elements that follow lanthanum, that is the next 14, they are called what? Lanthanides. So someone is asking you, what are lanthanides? The elements that follow lanthanum, which are picked out from the mainframe and put at bottom, those are called what? F block elements, and those are called what? Lanthanides. Why are they kicked out? Because after entering 5D, your 5D1 here, this must be 5D2. That must be 5D2, but instead it is entering what? F. So I have to maintain the harmony of the periodic table and I have put it down. So without any confusion, lanthanum is a D block. Lanthanides are F block. And they vary from 58 to 71. And after they fill this, they climb up again. And this 72 will be D2, D3, D4, D5, D6, D10. Look at the harmony. This is 5D1. 72 is 5D2. Then 5D3, 5D4, 5D5, 5D6, 5D10. Wow. There is a decorum. The harmony is maintained. It's maintained. After that, and I kicked this all F elements to the bottom, but remember, they also belong to what? 6th period only, but I have removed that and put at the bottom to maintain the decorum of the periodic table. Got my point? So what I will do, I just rub it off. So lanthanum is a 6th period element and it is D block. Elements that follow lanthanum, whose atomic number is 57, are called lanthanides. These are called what? Lanthanides, you must understand. Now these lanthanides, the feature is they also belong to 6th period. Electrons enter 4F instead of 5D. Instead of what? 5D. So, removed from mainframe and then put it at the bottom. Remember, this is cerium 58 to 71, that is lutetium, that is 71, that is 71. These are lanthanides. And they belong to 4F. So we have located the lanthanides. Now what is lanthanide contraction? What is lanthanide contraction? Let us discuss. What is lanthanide contraction? Now what we will do, once you can know this, let me fix it up. Lanthanum is 6th period and it's D block. Elements that follow lanthanum are lanthanides. And lanthanides are basically F block elements. And they belong to 6th period. and electrons enter 4f instead of 5d. People wanted to ask me this question. Why electron must enter 4f without entering 5d? That's a question what people ask normally. We wanted to ask rather. Well, I ask this question on behalf of you. You say that instead of entering D2, they have entered 4f, hence you kicked out them in the periodic from the mainframe. Well, remember, while writing electronic configuration, the expected thing is they are supposed to enter D, but they enter F, indicating that it's a common sense. It's a common sense that the energy difference, and why such a thing will happen is I can write it here. The energy difference between the 5D and the 4F is basically too small. The energy difference between the 4F and 5F is absolutely too small. So you cannot restrict an electron from entering into 4F after all, because the energy difference between them is very less. So when you're climbing a step, you're supposed to raise your leg like this and climb. In walking, I'm not raising my leg. You must understand. So it's almost flat. So any law or principle can't predict where the electron goes if the energy levels are matching like this. After going into the energy level, it will say hi to you. You can't guide through a principle that you go there, you go here when the energy levels are what? Equal. You must understand that. So lanthanum is a D block, which is atomic number 57. This is lanthanum. We expect 58 here, but rather you get 72. You rather get what? 72. And here it enters 5D1, and this is 5D2. Remember, that is 5D2. And what happened to the missing elements? They enters 4F1 and to 4F14. That means the energy difference between the 5D and the 4F is very less. So after entering, it will tell you hi. Nothing can predict, no rule can guide them. No principle can guide them. So let me conclude before I go to lanthanide contraction. Lanthanum is a 6th period D block element. Elements that follow lanthanum are called lanthanides. And mind you, lanthanum belongs to 6th period. Even lanthanides also belong to 6th period. But lanthanum, the electron enters 5D. In lanthanides, it is entering 4F. And the elements that follow lanthanum are called what? Lanthanides. And lanthanum itself is a D block element. Now let us discuss what is lanthanide contraction and its applications. Shall we? Right. This is about lanthanides. I have actually fixed the position of lanthanides and made you understand where the lanthanides and which block they do belong. Right. Now let us see lanthanide contraction. Let us see the lanthanide contraction and its applications. Watch carefully here. Watch carefully. This question will be asked in exam. And this is 100% sure. 100% sure is lanthanide contraction and its applications. And I'm telling you, you will get a question on this. Lanthanide contraction, that's for sure. Right? And what is lanthanide contraction? Let us understand. So, in lanthanides, watch carefully here. In lanthanides, 3 subshells are being filled. 3 subshells are being filled while writing in lanthanide configurations. If you write the configurations of lanthanides, not lanthanum. Lanthanum is a D block. Must understand that. It's a D block. Right? And now what I'm telling is in lanthanides configuration, 3 subshells are being filled. 3 subshells. One is ultimate subshell, that is NS. Penultimate that is N minus 1D, and this is anti-penultimate, that is N minus 2F. So the general configuration is, since it belongs to the 6th period, right, the general configuration would be NS2, it is filled, the 6th period, the S block is filled, and then N minus 1D, 1 to 10, that is also filled, that is 57, and next comes what? 72, 73, 74, that is filled. And now this anti-penultimate, that is N minus 2F, 1 to 14. I write it here properly. Watch. The configuration of lanthanides will be NS2, N minus 1D, 1 to 10. And the anti-penultimate, that is N minus 2F, 1 to 14. That is the general configuration of what? Lanthanides. Watch carefully here. This NS is basically the 6th period S block element, 6S1 and 6S2. 6S1 and 6S2. And D block is also filled. The D is also filled. You must understand it's N minus D, 1 to 10, and N minus 2F. So there are 3 subshells being filled what? In what? F subshell, you must understand. So that's for lanthanides. Lanthanides, right? And then watch carefully, in all these, bulk of electrons added to F. Watch carefully here. In lanthanides, there are 3 subshells being filled: ultimate, penultimate, and anti-penultimate. And bulk of the electrons, when you write the configuration of 58, you will actually get to know the cerium to lutetium. The bulk of the electrons are being added to F. The electron is entering F, it's not entering D. It's supposed to enter D. But rather, after lanthanum, it's entering F. F1, F2, F3, F4, F5, F6, F6, F14. You must understand. In fact, the D electrons are very, very less rather. You must understand here. It's a 0 or 1, that's all. Right? The S is filled, but only lanthanum you will find what? The D block. After that, the bulk of the electrons are basically added to what? F block. 4F1, 4F2, 4F3, 4F3, till it fills 4F14, then climbs up, then there is absolutely no chance of D. So even though 3 subshells are being filled, the bulk of the electrons, most of the electrons are added to F. The bulk of the electrons are added to F. And remember, since bulk of electrons added to F, F is a poor shielder. F is a poor shielder because of its peculiar diffused shapes. The F has pores. So the nuclear force of attraction, when you move from lanthanides, from cerium, the bulk of the electrons are added to F subshell. And F being a poor shielder due to peculiar diffused shapes. That means F has what? Pores. So what I'm doing, I'm demonstrating it to you. You start from, let's walk in the lanthanides. Lanthanides are from what? Cerium, and they go to lutetium. So what we are doing, start from cerium, F1, F2, F3, F4, and finally F14. The electrons are added, the bulk of the electrons are added to F. So when I move from cerium to lutetium, the atomic size is increasing. atomic radii is increasing, the nucleus is increasing, the nucleus size is increasing, so the nuclear force of attraction also increases. But the electrons are added to the F subshell, then the electrons are added to the F subshell. When they are added to the F subshell, they are not good shielders. Then the nuclear force of attraction penetrates through this F, and falls on the ultimate shell, that is nothing but what? NS. So thereby the outermost ultimate shell is pulled inwards, resulting in a contraction. That's nothing but Lanthanide contraction. You must understand. You must understand. If I can draw a pictorial representation of it for a better understanding, it looks like this. Watch carefully here. Walk in lanthanides. That is 58 to 71. That is from cerium to lutetium. You walk in them, left to right, you walk. This is cerium and this is lutetium, and here it is 4F1 which is filled. This is F2, F3, F4, and like that F14. You must understand. Here is the nucleus. I also draw the nucleus. This is the nucleus. This is the ultimate shell, that is NS. This is outer shell, that is the ultimate shell. In between, you have this F subshell. F being filled. F being filled. So when I walk, I start from cerium. When I walk, right, one electron is filled here, that is F. Walk another electron, F2. And thereby the nucleus is also increasing. This is cerium, next element, I add an electron here. Next, the nuclear size is increasing, I add an electron here. Like this, the nuclear size is increasing, and the electron is added only to F subshell. You must understand. So when I walk from left to right in lanthanides, you can see the nuclear size is increasing, but the electron is added to the F subshell only, till F14 are filled. But F being a worst shielder, the nuclear force of attraction penetrates. It penetrates and falls on the outermost shell. It penetrates. It penetrates through the F and falls on the outermost shell. Because you are a poor shielder, because of your peculiar diffused shapes, you have holes. The nuclear size is increasing. You are not shielding, so the nuclear force is penetrating, falling on the outermost shell. So if I take one step, cerium to the next one step, then the outermost shell is pulled inwards. Second step, pulled further inwards. Third step, pulled further inwards. Fourth step, pulled further inwards. Like that 14 strides if you take, the outermost shell is pulled inwards, resulting in a contraction which is called lanthanide contraction. You must understand. So when you walk in lanthanides from cerium to lutetium, the nuclear size increases, but the electron is actually added to F and not D, and the ultimate shell is being pulled inwards, resulting in contraction, which is called lanthanide contraction. You must understand. So if you can define, it is like this. The contraction observed in lanthanides, the contraction observed in what? Lanthanides, which is nothing but the 4F series, observed in lanthanides from left to right. The contraction observed in lanthanides from left to right due to very poor shielding effect. Shielding effect of F subshell is called the lanthanide contraction. You must understand. Is called the lanthanide contraction. You must understand. If the contraction is simple, we would have discounted it. Yeah, okay, there is some contraction, discount it off. Atoms are invisible. What are you talking about? Why are you so concerned about this contraction? It is ridiculous. What is that you are doing? Let them contract. Where is the decorum lost? These questions might arise. Don't be trivial. If you do a business with 1 paisa, 10 paisa, if you will lose 1 paisa, it is too much. And it's not trivial. The contraction is too much. The contraction is too much. And the shielding effect of F is so worst, you can't discount. You can't discount. And I can give you some values rather. If I give you some values, look into the way it has actually decreased. The way it has actually decreased, you must understand. It all starts, right? You know, the decrease, if I can put on an average, you said, can't you discount it off? It is so less. Yeah, what will happen if you discount? And all these things, let me tell you. Average contraction if you see, average contraction, right, is around 0.2 angstrom units. Average, you take the average contraction. Well, first of all, the atom is so small, and 0.2 angstrom units decrease is almost 1/5 of the sizes of the average sizes of the atom, which is not discountable. It is a serious issue. It's not a silly issue. It is a serious issue. If I can write the proper values to you, if you actually see the proper values, it all starts from cerium and ends at lutetium. And if you look into the way it has done, it is 187 picometers. It starts approximately 187 picometers. You can check the actual values in your Clark tables. It starts from 187 and it will be ending somewhere around 174. And this is a regular decrease. Regular decrease in the lanthanides. You start from 187 picometers. Pico is 10 power minus 12. And you decrease to 174. And the average contraction noticed is around 0.2 angstrom units, which you wanted to have an idea. These values are for no discount. You can't discount them. You cannot discount them. No, absolutely not. You can't discount them. Must understand. Right? Observe carefully then. If that is the case, then what are its consequences? You're not discounting because you have a lot of consequences, right? And the consequences are nothing but the applications which you're supposed to get it in the exam. Let me check it out. The consequences. But before I check, this is what I'm writing. The contraction observed in lanthanides, that is 4F series, from left to right due to poor shielding effect of F subshell is called what? Lanthanide contraction. And you can't discount these values. That is around 0.2 angstrom units, or approximately it decreases from around 187 picometers to 174 picometers, which I consider to be considerable decrease because of the worst shielding effect which we notice in F block. Right? And let us see its applications now. Watch carefully here. Consequences of lanthanide contraction. Consequences of lanthanide contraction, you must understand. Now, since there is size decrease, in 4F, that is the lanthanides, many things have a role. When the size decreases, then look at the density. When the size decreases in 4F, when you move from left to right, that will have a direct bearing on density. Direct bearing on density, because when the size decreases, the density must increase. And there is a considerable increase. It's not a small thing. You can't discount. Don't make it trivial. If I can give you the approximate value for it, the density is basically increasing from 6.1 grams per centimeter cube to, it's almost increasing to 9.8 gram per centimeter cube. So there is a density increase. So the question which he will ask in the exam is, which of the following is true? The direct consequence of lanthanide contraction is the density is increasing from 6 to 9 because the size is decreasing. The density would like to increase. Direct bearing of it. And even the second consequence is the melting points. This is too much. You asked me to actually discount it. You asked me to discount the contraction. What is there, man? You're shouting. Why don't you discount it off? It's a small increase and all. Look at the density. 6 to 9.8. And look at melting points now. The melting points actually 1193 Kelvin and they almost grow to 2000. Look into this. You want me to discount it? You want me to discount 1100 Kelvin to 1925 Kelvin? You can't discount, man. You cannot discount. Lanthanide contraction on an average is 0.2 angstrom units. Oh, too less. Discount it off. Why are you making a big issue? Well, I make it a big issue for the simple reason. Look into the densities that vary in lanthanide. 6 to 9. Considerable. Considerable. And the third consequence, after the melting points that vary from 1193 Kelvin to 1925, and the next one is zirconium and hafnium have same radii. They have same radii. They have same radii. Now, what is zirconium? What is hafnium? First of all, what is zirconium? What is hafnium? What is hafnium? Remember, what is zirconium is? This is the 5th period element. And this is the corresponding 6th period element. That means that if I can write this is lanthanum 57. This is lanthanum. That's lanthanum. The next element is hafnium. The next element is what? Hafnium. If I can draw it somewhere here. Watch carefully here. Watch carefully here. Watch carefully here for better understanding. This is the 5th period. This is the 6th period. And this is the lanthanum. This is the D block. This is lanthanum. Here the electron entered as D1. The next element, which is supposed to be 72, is hafnium. It's hafnium. Hafnium is basically 6th period. And the corresponding 5th element is zirconium. So this I'm speaking of. So zirconium is 5th period, hafnium is 6th period, and zirconium and hafnium both belong to D block. Both belong to D block. One is 5th period, the other is 6th period. Now you tell me. This is 5th period, this is 6th period. Just below zirconium is hafnium, no? Just below zirconium is hafnium. What we were told, in a group size increases. In a group size increases. And this is a D block. Below zirconium is hafnium. So we expect a size increase. But what happens? The size of zirconium and size of hafnium is same. If you ask me why, between 57 and 72 there are 14 elements which are placed down. 58 to 71. There the size decreased, and then climbed up. So from 58 to 71 you find lanthanide contraction. So the size considerably decreased. Then you climbed up as hafnium. Then the size increase is not reflecting. And remember that zirconium and hafnium have same radii. And if you say zirconium and hafnium approximate values, if I can give it to you, it is 155 picometers and this is 159 picometers. Come on, man. Come on. This is same. 158 and 159, same. Come on, what is this? Because zirconium is below hafnium, you must expect a size increase. Too much size increase. But 58 to 71, you have the size contraction, and then climbing up, you will find that the zirconium and hafnium will be having the same radii. This question is asked many a number of times, 100 times you will get it in exam. The direct consequence of lanthanide contraction is zirconium and hafnium have same radii. And also I would like to say two things about them. Watch carefully here. First thing and first, zirconium comma hafnium, they have same radii. If I can give you the zirconium and hafnium radius, you can actually see one is 155 picometers and the other is 159 picometers. And remember, zirconium is tetravalent. So if you put the ionic radii, hafnium is also tetravalent. If you look into these things, this is around 84 picometers and this is 87 picometers, and the ratio of all this is almost equal to 1. Look into this. This is ionic radii. And this is the radii. This is ionic radii. Zirconium, hafnium have same radii is a direct consequence of lanthanide contraction. Look into this. You asked me to discount. Am I looking silly? You can't discount. 0.2 angstrom, come on, leave it off, and you leave it off. Then I have density increasing, melting points increasing. Then you have zirconium and hafnium. Zirconium belongs to the 5th period and hafnium belongs to the 6th period, corresponding below each one of the other. But still the sizes are same. Ionic radii is same. You know, in fact, the issue is very strange. Very strange, I would like to mention. Hafnium was discovered first. After 134 years, come on. Hafnium was discovered first. After 134 years, zirconium was discovered. If you ask me why, let me tell you, the sizes are so same. When the sizes are same, one will be the impurity in the other. They don't exist separately. I prefer to combine with the same fellow of the same size of mine. So zirconium is hiding in hafnium. We are fools. We are looking at zirconium separately, which was not there. In fact, the zirconium was discovered 134 years later of hafnium. That means we are searching zirconium where it is. And the search went on for 134 years. Ultimately, we found it in hafnium. And one element is found in another element as an impurity. And the basic condition for impurity is, the sizes must match, and the zirconium and hafnium have same sizes. And later the zirconium was separated from hafnium, not individually, indicating lanthanide contraction is a reality. It's a reality. Must understand. Look into the lanthanide contraction consequences. Density increases, melting point increases. 5th period element corresponding with the 6th period element having same sizes. All these are questions in exam.